Welcome to the first of the quarantine series. Special lecture series here for Chem 357 thermodynamics about electricity, solid state physics. How does electricity work on the atomic level? How do batteries work? How do diodes work? How do solar panels work? All of these things can be explained at the atomic level. And to start off here, I'll show you a way to intuitively think about electrical circuits and the flow of electricity, which is really just the flow of electrons through a material. And it behaves very similarly to the flow of water through pipes. And all of these things are often not only analogous, but both qualitatively, but also sometimes, quantitatively. So this is a very useful analogy. But you know that if you take water to some high altitude, such as you can pump it up into a water tower, then it will flow to a lower elevation. It will convert its gravitational potential energy from being at a high altitude into kinetic energy as it flows down to the Earth's surface or into your home. The potential energy, of course, can be calculated with the mgh formula. So the potential energy is proportional here to the height of the water tower. You can measure a flow rate of that water. How much water maybe passes through some cross-section here of the pipe per second. This is directly analogous to the current that you can measure from the flow of electrons in an electrical circuit. And it is restricted by the same sorts of things. You can imagine here, if you have a wider diameter pipe, you will get a higher flow rate. And the same is true for a circuit. A wider diameter wire will have a lower resistance. There is more space for electrons to flow through. If you restrict your water with little holes like this shower nozzle, which is for some reason attached to this water tower, you will increase the resistance of your circuit and decrease your current, keeping the same voltage, since your height difference of your water tower and your surface are the same delta H there. So if you can kind of imagine what sorts of things restrict the flow of water, you can imagine what sorts of things restrict the flow of electrons. Here's your analogous circuit. In the definition of conventional current is that it flows from the cathode to the anode of a battery. However, keep in mind that conventional current was sort of defined before there was any real understanding of what was going on here at the microscopic level. And the definition turns out to be the opposite of the flow of electrons. So electrons are actually flowing this way in this circuit, so that's something to keep in mind. But practically it doesn't make much of a difference for this picture, which way you define the flow here. The current will flow through here an object with a high load. This is a incandescent light bulb here. This is the same as our shower head, This one little piece of the circuit here is restricting the flow, is the rate limiting step of the flow, if you want to think about it in a kinetics standpoint. And so this slows down the flow of water everywhere, not just at this point. Okay, because this is the rate limiting step here. This is also the case for putting something like a light bulb in your circuit. And in fact, this is directly analogous. The reason this incandescent light bulb has a high resistance is because the only thing in here is literally this very thin wire of tungsten that is very thin purposefully to increase the resistance of the current that flows through it, because you get resistive heating of that filament, and so it will heat up very, very hot. It is made of tungsten because tungsten has one of the highest melting points of any material we know here on Earth. The hotter you can get this filament, the brighter the light that it will emit in the visible region of the spectrum. And the point of the bulb is just to keep that filament in an inert atmosphere, because if it was exposed to the air, oxygen would oxidize it very rapidly at the high temperatures that it gets to, which is over 1,000 Kelvin. And it would just burn up. And so you need to keep it in an atmosphere of something like argon. So this tiny filament restricts the flow of electrons here, but the electrons will still flow to the other end of the battery, and we have ourselves a complete circuit here. The electrical potential energy, similar to this potential energy equation for the water tower, is dependent on two things. It's dependent on the magnitude of the charge that is separated times the voltage of your battery. Here the charge that is separated would be normally the charge of an electron. Or if you wanted to calculate the sort of total energy content of the battery, this would be the sum of all the charges of the electron, of all the electrons. The voltage of the battery depends on the oxidation reduction reaction that is taking place inside of it, that you are exploiting to generate this electrical power. We will talk about that later, but you should have been exposed to the standard reduction potentials of different materials, and in Chemistry 151, and how you might go about calculating the reduction potential of a reaction. An important equation that you've probably already seen that governs electrical circuits is Ohm's law, V equals IR, where V is the voltage of the power supply, here the battery, I is the magnitude of the current, and R is the resistance of your circuit. So you can see for a fixed potential battery, as you increase the resistance, the current has to go down, and vice versa, as we have already discussed. Units are, as always, of utmost importance. And these ideas we've been talking about before of force and energy, which have units of newtons and joules, have a electrical counterpart, which are the same ideas but on a per charge basis, since often this is more useful in an electrical circuit, is the force that is acting upon a single electron, for instance. Since this is what governs what is going to happen is where the electrons are being pushed. The per charge form of force is the electric field. Thus it has units of newtons per coulomb. And the per charge form of energy is the volt. This gives you your voltage or your electrical potential. What is the energy content of a single electron in your circuit here? And therefore, a useful unit of energy, a new unit of energy for us all to enjoy, is the electron volt, which is defined very logically as 1 volt times the charge of 1 electron. Okay, so it's the potential energy of 1 electron held at a 1 volt electrical potential. You will see this unit often in solid state physics, since the whole point of calculating energies of electrons is to figure out the voltage of your circuit component. Voltage arises from a separation of charge, which is generated by an oxidation-reduction reaction within the battery. The anode of the battery has a negative charge. The cathode of the battery has a positive charge. And electrons here will, these extra electrons on this side will flow through a wire to the positive side, creating your current. Remember, of course, that the conventional current is defined as flowing in the opposite direction the electrons are. So let's look at current on a microscopic level here. So we've got some extremely thin wire, which is, we have a bunch of atoms here in the metal, and you have electrons on each one. And the current is defined as the change in charge over the change in time. Or more specifically here, if you divide this wire, if you kind of put a boundary through this wire somewhere here, how many charges pass through that surface per unit time? And so the unit of current is an amp, which is equal to 1 coulomb of charge per second. And since the charge of a single electron is 1.602 times 10 to the negative 19 coulombs, there's a lot of electrons that need to flow through per second. And an amp turns out to be a pretty large amount of current. There's a video here that I will not, play because of copyright reasons, but here's the address on YouTube. That it's kind of a fun video that asks, what is traveling faster, a snail or an electron in a circuit? And you might be surprised by the answer. It turns out there are there are 2 different velocities that are important for electrons when we're talking about circuits here. One is the drift velocity, which is for a single electron, how fast is it on average moving one way or the other? And that is pretty slow. There's another velocity called the Fermi velocity of the electron, which is it's based on its average kinetic energy within an atom, or within the whole network of metallic bonds in a metal. And that is quite fast. And so the reason those are different is because the electron in this circuit is moving around in a lot of different directions, but is only moving in one particular direction. Is only drifting in one direction, very slowly on average. We'll get into a discussion of that here shortly. But if you want to calculate a microscopic current here, what you first need to know is the force that is acting upon each electron. That will determine how fast it's moving from along your wire. And we've talked about how the electric field gives you the force per charge. So we want to calculate this electric field E. And that's going to be equal to your voltage divided by the length of the wire. Why is that? Well, you know that work, form of energy, equals force times distance. And the same is true on a per charge basis. Voltage, which is energy per charge, is equal to the force per charge times distance, which would be L here. Okay, so this is just a rearranged form of that. So we've got our length of our wire. We've got the voltage, electrical potential across our two points of the wire here. And so what would the force on each electron be? It would just be the charge of the electron times the electric field, since this is just defined as the force per charge. Okay, so we have the charge of an electron. This is the elementary charge constant. And if you know the force, you can calculate the acceleration on the electron. Force simply equals the mass times the acceleration. And you can solve that for the acceleration. Here's your force. You can imagine this is mass times acceleration here. The mass has simply been moved to this side of the equation. This is the mass of an electron. This is also a constant. Both of these numbers here are constants. So the acceleration is proportional to the electric field. What if you want to calculate the velocity of the electrons? This will be directly related to the rate at which electrons will pass through some point along the wire. Well, if acceleration, is in units of meters per second squared, velocity is in units of meters per second, you need to multiply the acceleration by a time in order to get to velocity. This tau is the time over which electrons are allowed to accelerate. It turns out that electrons will not continue to accelerate. They don't just get faster and faster as they flow through the wire. They end up only having some small distance that they can travel before they are stopped and have to start accelerating again. You can imagine the electron moving through the metal, and every once in a while it bumps into an atom or something like that. So it is not just traveling in one direction, it is actually bouncing around between atoms, allowing you to calculate some average velocity in a particular direction that is roughly constant, which would be the acceleration times the amount of time that it is allowed to move before being disrupted. This velocity we are calculating here, v sub d, is the drift velocity. That is the average velocity that electrons are moving in some direction through the metal. We can also, the electric field is not a parameter of our circuit. We know expressing this in terms of voltage and the length of the wire is more convenient. These are things we will usually know. We will know the voltage of our power supply, be it a battery or some other type of power supply, and we will know the length of the wire, and so we can substitute this in for the electric field to get a more useful expression. We've still not quite arrived at an equation for current, which is equal to the number of charges that flow through some cross-section per unit time. But we can get this from the velocity if we just think about things logically and consider our units. Velocity is in units of meters per second. And we need to get this in terms of charges per second. So if we multiply it by these three variables, we will achieve that. And these variables are 1, the charge of the electron E. This makes sense. N, capital N here, is the free electron density of the material of the wire here. It's the number of electrons per cubic meter of volume of the material. This makes sense if you think about it in terms of the liquid flow analogy. If you have a denser liquid, more molecules of that liquid will flow past a certain cross-sectional area of the pipe per second, just because they're packed tighter. It doesn't have to, flow as quickly to get it through. Also, another variable that this depends on here is the cross-sectional area of the wire. For instance, if we have 2 rows of sort of atoms that electrons can move between here, the current will be twice as fast. And as we increase the area, the current will flow proportionally. There's just more room for electrons to flow, just as if you increase the diameter of a pipe, the flow rate also increases. So these all make qualitative sense, and they make quantitative sense in terms of working out these units. So you should pause the video and work out these units for yourself. If we substitute in our expression from the previous slide for the drift velocity, we obtain this equation, which is starting to look more complicated, but is still dependent on very reasonable variables. We can rearrange this expression, same one we had on the previous slide here, because this is looking familiar. Remember that our electrical circuit equation that I told you on the first slide is V equals IR, Ohm's law. And here we have V, and we have I, and so all of this must be 1 over R. So we can move that to the other side of the equation, and we can say that that equals the resistance of the wire. So we're beginning to come to an equation that gives you a microscopic definition of a current, or of a resistance. It is useful to separate this term further because there are some properties in this term here that are dependent on the nature of the wire, the shape of the wire, the length and the cross-sectional area of the wire. And there's another bit that is dependent on the material, which would be the electron density and the tau, the time over which the electron can accelerate unimpeded. And so the length and the area are separated out here often, leaving us with rho, which is called the resistivity, and this is dependent only on the material. So whereas you can have a copper wire with different resistance values depending on its length and then the diameter of the wire, all copper at a single temperature, in a single sort of crystal structure of copper, will have the same resistivity. This is a property of the material. Mass of the electron, elementary charge, these are constants, but the resistivity is dependent on the free electron density and this tau, this time of between electron collisions. There's also a inverse value called conductivity, which is sometimes used, which is just 1 over the resistivity. So if you see this sigma, or you see conductivity being discussed in the literature, this is all it means. We can express this even more fundamentally by taking this tau and expressing it in terms of something called the Fermi velocity of the electrons in that material and the mean free path, which is the distance between collisions. Since velocity equals distance over time. And so now we can write our equation for resistivity like this. The Fermi velocity comes from the sort of band structure of the metal, and we will talk more about this in the maybe the next lecture, certainly in the next 2 lectures. And this mean free path is related to the distance between atoms in the metal. That's well, there's a lot of complexities to lambda, I guess I should say, but it is certainly related to the crystal lattice of your material. And this depends strongly on the temperature. So imagine this. Well, first, what happens to the resistivity as you increase temperature? For a metal, resistivity increases with increasing temperature. So your mean free path is getting shorter. Why would that be the case? Well, imagine, I feel like there's a game or something I want to relate this to, but I can't think exactly what it is. But imagine you have an electron just walking in a straight line through through a bunch of other people, I guess, maybe through a crowd. Maybe that's a good analogy. And imagine everyone in the crowd is standing still. If everyone in the crowd is standing still, which would be analogous to your material being at a low temperature, they're not moving very much, you can sort of see maybe a path through them through which you could walk in a straight line unimpeded. Especially, in a crystal lattice where all the people are sort of regularly spaced. This would be analogous to what happens to an electron at low temperatures. That you can just kind of walk between the people and you won't be stopped. But now imagine that the people are moving around rapidly like they, normally are in the world. And you are trying to walk between them, but you keep having to change direction to dodge around them, or maybe they're even bumping into you and changing your direction. This is decreasing your mean free path. It is now taking much less time for you to bump into another person and then have to sort of change direction and stop and reaccelerate and so forth. So that is the origin of the temperature dependence of this parameter here. All right, I think that is a good amount of content for this video. I guess one final thing here is the Fermi velocity is related to the what's called the Fermi energy, which is something we'll be discussing here shortly. This is just you can think of this as the kinetic energy of the electrons, which would be 1/2 the mass of the electrons times their velocity, the Fermi velocity squared. Here are some key points here. Remember, voltage is electrical energy per charge, and electric force is electrical force per charge. These are the per charge variations of things that we use frequently. The free electron density in a material is the number of free electrons per unit volume. It is important to specify free electrons, often meaning valence electrons or the electrons in the highest energy suborbitals. You know, the core electrons of metals in particular are buried beneath several shells of electrons and will not move away from from the atom, from the nucleus of the atoms. The outer electrons, however, are free to move. A material with a high free electron density has a high conductivity. This makes sense. And resistance is determined by the resistivity of the material, as well as the length and cross-sectional area of your wire, or whatever is conducting your electricity. I'll see you next time.